In the last video, we looked at how to calculate stress and strains on a symmetric laminate that had in-plane loading. And for that, we just assumed a stress resultant n sub x. But in this video, we're going to see how we can take certain kinds of structures and calculate what those stress resultants need to be. So again, we looked at a flat plate just under a tensile loading, and so finding n sub x was pretty straightforward. But there are a lot of other structures like torsion tubes and pressure vessels that we can approximate with those equations that we've developed. So one thing that as we start to look at these to keep in mind is that our assumption here is that in all these cases that the thickness of the laminate is small compared to the other dimensions of the structure. So that means that the strains in the laminate are going to be the same throughout the thickness of the laminate. So if we have bending, that's not going to apply here. Structures like a thick wall pressure vessel, we know that the stress and strain are different on the inner surface than they are on the outer surface. But if it's thin wall pressure vessel, then making the assumption that the strains and hence the stress is going to be the same throughout the thickness is a reasonable approximation. So let's go ahead and look at a couple of different types of loadings, different structures. So here's a tube, and it's going to have a bending load on it. So this bending moment M. The nominal radius of the tube is capital R, shown here. And from mechanics of materials, we know that a body that's under bending is going to have maximum or extreme values of stress, mc over I. So in this case, the way we've drawn this would be a tension at the bottom, tensile stress, mr over I, with r being the distance away from the neutral axis in this case. And up top would be the same magnitude, but that one would be compression. So again, the sense of the moment that's shown here would be tension on the bottom, compression on the top. Now for a thin tube, that moment of inertia I can be approximated as pi r cubed times the thickness. So we substitute that into the expressions for the maximum and minimum stresses, and we get the expression that's shown here. Now, to find the equivalent stress resultant at the top and at the bottom, we simply take the stress and multiply it by the thickness. And so that gives us this expression for n sub x, m divided by pi r squared. And again, at the top, that would be compression, and at the bottom, it would be tension. Usually it's going to be the negative value that we're going to look at that's going to be critical, because the compressive stress of composites is almost always going to be lower in magnitude than the tensile strength. And so the compression is critical. Now let's look at a tube that instead of bending has a torsional moment applied to it, or a torque. Well, with that torque, that if we had an isotropic tube, it would give us a shear stress of Tr over J, and J being the polar moment of inertia, and the approximate value of that is twice of the I value, in other words 2 pi r cubed times T, if the tube is thin. So Tr over J, plug that in, and now again the stress resultant, in this case n sub xy, we get by taking that average shear stress and multiplying by the thickness. And so there's our value for nxy. It's the torque divided by 2 pi r squared. Now another structure that we see quite often when we have a bending loads is to make what we call a sandwich structure. So we take a low density, usually low cost core as well, and put it in the middle of two composite skins on the top and the bottom. And so the idea here, of course, is that the moment of inertia goes up greatly as you can separate those composite skins. And so again, you can certainly make a lighter and less expensive composite that's resistant to bending by putting some kind of a core in there. Now it could be balsa wood, could be foam. A lot of aircraft structures use aluminum honeycomb in the middle. But again, for bending structures, this is a very efficient structure. Now, if those composite skins are thin, we can approximate by saying, okay, it's just tensile stress on the bottom, compression stress on the top. And again, if they're thin enough, we'll just assume that the stress is constant over the skin itself. And just like int of x is a force per unit width, m of x is the moment per unit width. Now, a little bit different nomenclature than what you may have learned in mechanics of materials. When you talk about plates and shells, when we say m sub x, it's not a moment about the x-axis, but rather it's the moment resultant of stresses that are in the x direction. So again, we can look at these int sub x's and the distance apart and say that will result in a moment, m sub x. And m sub x is just going to be, it's just a couple here, so n sub x times h would give us the moment. And so n sub x is simply equal to m sub x divided by h. Now once again, we could say plus or minus on that as well, because it's going to be tension on one side and compression on the other, and it's usually going to be the compression side that we'll consider to be critical. And again, a couple of approximations that we've made there. One is that we're not even going to worry about the stiffness of the core. It's usually going to be so much, the stiffness value is going to be so much less than it is for the composites that it's okay to ignore it. And again, the fact that the stress is going to be constant within each skin just means, yeah, those skins have to be thin. The next section of the notes, by the way, we will look at the bending of a symmetric laminate, and we'll see a more exact method. But this is a pretty good starting point, especially for like preliminary design. And so one more to look at that we run into quite often, and that's pressure vessels. We're looking at a cylindrical pressure vessel with closed ends. We're just looking at the cylindrical body of that right now. And so if we take a piece out of that, in mechanics of materials, we know that we have an axial stress, PR over 2T, and a hoop stress that's twice that, PR over T. And so we're calling the axial direction X and the hoop direction Y in this case. And again, in both those cases, we're just going to take the stress, multiply by the thickness to get the stress resultant. And so in the axial direction, int of X is going to be PR over 2. And so in the hoop direction, it's going to be sigma y over t, which is just going to be double the axial value, and just PR then gives us the stress resultant in the hoop direction. So again, that shows us how to find the stress resultants for a lot of different types of structures. And in the next video, we'll start doing some examples. We'll look at a torsion tube. We'll look at a tube that's under torsion and bending, and look at doing some design work and some optimization of design as well.